Hello. Today I'm going to be presenting a work titled Learning Without Picking Secure Multi-Party Computation Genetic Programming. Let's dive into the details. So, to start, let's briefly talk about genetic programming. GP is a powerful technique that evolves program to solve complex problems, making it useful in areas like predictive modeling, fault localization, and optimization. However, these applications often involve sensitive data such as medical records, financial information, and proprietary data. Ensuring the privacy of such data is crucial for compliance and to prevent unauthorized access. Now, secure multi-party computation or SMC is a method that allows parties to collaboratively compute a function over their inputs without revealing these inputs to each other. The researchers implemented SMC using the obliv framework. The motivation for this research is very clear. As GP often involves sensitive data, it's essential to perform computations in a way that maintains the data privacy, allowing multiple parties to work together without exposing their data. Now, let's explore the multi-party data holder scenario. Here, different parties hold different parts of the training dataset. Let us call the data holders data parties and the mediator who is running the genetic programming the GP party. The GP party generates candidate solutions and an obliv SMC program, which is then distributed to the data parties. These parties securely input their data. The fitness function evaluates the solution securely, and all parties receive the final result. This diagram here illustrates the data flow and interaction between the parties. Also, there is a part where single party data holder scenario where only one party has the data. It can be easily implemented by making sure uh, easily implemented by making the GP party act as the data party, the second data party with no training dataset. The GP party executes the GP process, generating and sending the SMC program to the data party, which then securely inputs their data. The results are shared without revealing any of the data. The Next, we can look into the research questions here. The researchers here aim to answer two main questions. First, how effective is SMC GP compared to normal GP? And second, what is the runtime overhead of SMC GP? To answer this, they use symbolic regression benchmark and a real-world fault localization dataset. They measured mean squared errors for accuracy and wasted effort for efficiency. The result of this the results show there is no significant data difference in accuracy between SMC GP and normal GP, confirming that obliv performs correct computations. However, there is significant runtime overhead was observed. SMC GP was up to 1739 times slower than normal genetic programming. This overhead is mainly due to the use of garbled circuits and communication protocols to make sure the data are secure. Those data are not revealed to any other party. Thus, while SMCGP ensures data privacy, it comes at the cost of computational efficiency. Now, for the next part, let's look at the paper, the strengths and weaknesses of the paper. The authors provide a detailed methodology for implementing SMC in genetic programming using obliv. They thoroughly describe both single and multi-party data holder scenarios. Also, the study includes a rigorous empirical evaluation using widely recognized benchmark programs and real-world data. This adds credibility to their findings. The paper also addresses a practical and relevant solved problem, which is data privacy in genetic programming. This is crucial for applications involving sensitive data. I would say the weaknesses are like there is a significant drawback in the high computational overhead of SMC GP, which is up to three orders of magnitude slower than normal genetic programming. This limits the practical usability. Also, the experiments were conducted on a limited number of datasets and scenarios. Broader testing could provide a more comprehensive understanding of SMCGP's performance across different applications. There is another thing, the use of oblique and the need for garble circuit introduce a significant implementation complexity. This might be a barrier for wider adoption of the technique. Overall, while the paper makes significant contribution to the field of privacy preserving genetic programming, these areas offer opportunities for further improvement and research. To conclude the presentation, I would say SMCGP allows for secure data handling in genetic programming without losing accuracy, though it does introduce significant computational overhead. This work represents a crucial advancement for privacy preserving computations in sensitive domains. Looking ahead, future work could explore adversarial scenarios where candidate solutions also need to remain oblivious and apply the SNC model to other evolutionary or algorithms. Thank you for your attention, and this concludes my presentation.